Hi, I'm Alan Ross, and this is a power panel from APC Media. My two guests today are Tony McGrail. Tony is an old friend of what we do at APC Media. He is a solutions director of asset management and monitoring. Has got a tremendous knowledge of that area. And also is with me is Nathan Jacob, and Nathan is the senior asset specialist for Camlin Energy. Gentlemen, thank you for joining us.
Pleasure to be here. Thank you.
Thank you very
So
much.
why don't we go with you, Tony? Tony, if you wouldn't mind, if you would, that's me. I'm the managing editor. Tony, would you just introduce yourself? They can read, obviously, but I want them to know who you are.
Sometimes, Alan, I run panels and I give people a 30-second management challenge to introduce themselves, as in people who aren't management just can go on for hours. So, Tony McGrail, bit of a checkered history. I spent several years in the US as T&D substation asset manager. Also spent several years in the UK as a substation technical specialist with National Grid. It was post-privatization, so we were farmed out as test engineers looking at transformers, breakers, doing partial discharge work around the UK and some of Europe. And previous education also includes being a high school teacher and being a maintenance software developer for BP.
So the greatest challenge you've had in your career was high school teacher, I imagine, right?
There was a lot of fun getting to be a high school teacher with how do you measure success and so on.
All right. And Nathan, if you can just take a minute to just share who you are.
Yeah, great. Thanks for having me. So my name's Nathan Jacob. I'm a senior asset specialist at Camlin. My position is that of a subject matter expert type role. So where I provide specialized support and guidance to customers in areas related to online monitoring and monitoring solutions. Also involved with the analysis and interpretation of data collected from assets, combining the online monitoring data with also data collected from other sources, testing, anything from factory acceptance testing to inspections and whatnot. Okay. My background before Camlin, I was a test engineer. So I was a field test engineer and laboratory test engineer with Manitoba Hydro for about 16 years. There I have, wide experience with testing in the lab, diagnostics, evaluating assets and the like.
All right, so two experts on monitoring and diagnostics, and that's why we asked you all to join us today. Let's go right on to the series of discussions that we've got. At the end, for those that are in the panel, you will be able to ask questions, and I will get them through the chat. But we already have a number of questions that many of you sent in when you registered, which is really, really good. So let's start with this, and I want to take it kind of then, now, when. Okay, this is where we've been, this is where we are, and this is where we're going. Let's first of all look at this whole area of monitoring and diagnostics when it really was just about the assets themselves. It was the transformer with a DGA monitor or the transformer with a bushing monitor. And we really, I know we all talked about the data, but we really never got into the massive amount of data that we've got. But talk a little bit about your experience and just your perspective on where we have been as an industry when we look at asset monitoring. And that would be for power systems, not just transformers. Let me start with you, Nathan.
Sure. Yeah. So, considering like monitoring in the early stages of monitoring, I think a lot of people conceive these as devices to really alert and alarm, right? Like the mentalities were similar to like protection systems, where it was just a binary states. Is the alarm alarming or not, and not using the data for much else beyond that. Uh, Now I think that there's a shift. So there's a shifting perspective where people are looking to gain first more value from the data they're collecting, and they're wanting to use this data to make maintenance decisions, condition-based maintenance, have not just the sense of early warning to failure, but to really optimize the asset. So if there is a way to be predictive in their maintenance and approach that, they're really focusing on that as well. Another key distinction today versus previously is that with greater integration, right? And like moving the data to the cloud and having better visualization of the data and better interpretability of the data. So with the data being more accessible and easy to visualize in a single interface, they can have their SMEs review that data more effectively and make better decisions on that basis. I think the last point I would make, one is that for single assets, like you mentioned the transformer DGA as a concept, there's also a lot of motivation to do more holistic monitoring. So combining sensors for different components on a single asset. So for power transformers specifically, it's the combination of the DGA monitoring with the partial discharge monitoring, with bushing monitoring, with monitoring of arcing and other system events and the like, and really having all that data combined in their analytics to make more effective decisions from that data.
Thank you. Tony, your perspective on where we've been up to about now.
I think it's a journey of what you might call a triumph of hope over expectation. Many years ago, when you got into condition monitoring, it was a box with lights on. It was something that they over there did. And over time, people have realized that this is a useful thing rather than an engineering toy. I'm going to ask Paula if she would show my slide number 21, just briefly. The reason being is this goes back with development at National Grid UK of a multi-gas DGA system 25 plus years ago. And it was in the real world, it worked, it did what it had to do. And the main concern I had was that the transformer that we were examining is a 750 MVA transformer, stretched 500 MVA design. It overheated substantially. My main concern was that to analyze the oil, I had to take oil out of the main tank to the left, take it into my little examination cabin, the white thing, which I would call a relocatable DGA device, not necessarily portable, but relocatable, where we did lots and lots of analysis and experiments with all the available devices that were on the market, plus our own devices. And my main concern was that the oil would leak out from that and get into the local reservoir, which would be feeding northeast London, and I'd be on the 6 o'clock news. So my own monitoring was to get up on the first night I stepped in the cabin and walked around the whole thing every 30 minutes. And what this does is it reminds me of not just the fact that we're doing something beautifully technical, but there are consequences if this thing goes wrong. And there are consequences not just if the data is not valid or correct or precise or relevant, but if we analyze it without reference to the context and if we analyze it just in independence. So what I've seen over the years is the move away from that condition monitoring being something that they do to being something that the organization does. And for organizations which are aware of, for example, ISO 55000 asset management, within that, there is a requirement that you monitor the performance of your assets. It doesn't prescribe how to do it, but it says, as you have these assets, you need to know which ones are in good condition and you need to know what the plans are for each asset. So that has changed, that context has changed things. So condition monitoring becomes a lot more vital for the whole organization, and it needs to be embedded in the organization. And people have to understand what value it can bring. When we talk to, for example, insurance companies, they will tell us that the big payouts that they have to pay for example, transformer failures or substation asset failures, it's not to do with the replacement cost of the asset, it's to do with the business interruption. So that identification, not just of the technical need, but the business need and the asset management context is hugely important in deciding which box with which lights, and then how we use it, what our expectations are, how to make sure that we get value from it, so we don't go from ignorance to negligence. That's a quote from a guy called Tommy Salmon, ex of Dominion Energy, now at GE. Because they did have cases where the data implied one thing and they did something else. Quote a guy called John Truisi, ex of NIPA, don't clog up my hard drive with your data. people who are making the decisions need to have something which is useful, contextual, and supports making a decision clearly. And that's grown over time as the organizations have developed. So that would be it.
You know, there's both of you made a point, and I think the point is extremely valid. Um, in the beginning, it was a maintenance person that kind of made a decision, right? And the maintenance person didn't know what to do with the information, so it was really them. You know, yeah, they're making me do this. And you mentioned ISO 55000. You know, I've got to give line of sight of these assets. We used in this thing when the equipment speaks, and that's really what we've started to see happening. We started to see that we expect, and this is true throughout all of industrial. This is not just power systems. This is everywhere. There are vibration monitors that can go on rotating equipment, and they are Bluetooth enabled. So if you have 1,000 motors in a plant, you can put these vibration monitors on, and they're inexpensive, and they will report data back to you. That's a lot of data coming in, and now people are saying, oh, and we're going to get heavily into this, but I want to go to we really had 4 questions streams we wanted to talk about. I want to go to the third stream first, because I want to talk about, and you both mentioned data, and don't plug up my hard drive with your data, that idea. Now there are different types of data coming in, and you mentioned it, Nathan. You've got, let's just take a transformer. You've got bushing monitor data. You've got partial discharge monitoring. You've got a DGA monitoring. Is there an integration of all of that data, or does it take the engineer to look at it all when you get an alarm to make a decision? So are we really listening to the equipment, or are we hearing different things from the equipment? And we've got to have a subject matter expert there to make that. And that's a big thing, because I know Tony, that's one of the things that Doble and I know Camlin is very getting heavily involved with, is to be able to give a solution to the end user, because those subject matter experts, there's not that many left they're all retiring. And they're looking for people like Doble and Camlin Energy to be able to take all of this data and help. So go from the idea of machines collecting data to data-driven decisions with subject matter experts. Tony, I'm going to start with you on that one. Where are we right now with that?
I think it depends where you look. So the whole role of condition monitoring is to provide data for supporting decisions. Now, these decisions previously were often made by default. If no one's complained that it's gone dark in their town, then our transformer in our substation is likely to be okay. So let's just leave it alone. Now that we have data, it behooves us to make sure that we do something useful with it. And it's also a case of there's no point in putting a condition monitoring device on anything unless we have some expectation as to what the numbers should be. If I may, Paula, could you show slide number 6, please? And this is very simple condition monitoring from something which is less abstract than a power transformer. This is from just an automobile, a car, and we're looking at the tire pressures. So is it the case here where I've got 4 tires, I've got 3 at 37, 1 at 39, did one of them rise or did 3 of them fall? So condition monitoring here on the tires is all about, in this case, saying, well, what do I expect it to be? If you could drop to the next one, please, Paula. One down. Thank you. So in this case now, I've got 4 tires, 2 at 38, 1 at 29, and 1 at 51. This is condition monitoring data. I have got it. It's valid. What on earth do I do with it? So not only do you have to have expectations, you also have to have a plan to respond. And to have a plan to respond, you need to know what levels or trends or diagnostics are included, such that you can then say, I need to go and do something now. And that plan has to be in place from when you install the monitor, because if it isn't, what will happen is you'll get an alert come in, and then you'll call a council of the wise, and we'll bring together and we'll start to discuss data and timescales and rates of change and consequence, and the thing will fail in the meantime. And you've got to be very, very careful that the condition monitoring is seen as something which is managed ahead of time. We used to say that there were two main reasons to do condition monitoring. One was to learn about the monitor, and one was to learn about the asset. These days is a third reason, and that's to learn whether the organization is capable of managing the whole of the condition monitoring process, from specifying a monitor through to gathering the information and making decisions with it. And that's a big if, because a lot of people are not prepared for this. They put the monitor in and it really is just a box with lights on. So I've probably gone on too long, but I would say that that data to decisions has to be thought through ahead of time. And people who are good at condition monitoring tend to be good asset managers as well. There is a corollary to that from a guy, Don Schubert, Marsh Insurance, used to say, people who are good at asset management are also good at condition monitoring. But the reverse, just applying condition monitoring does not make you a good asset manager. It just means you're good at spending money. So you have to be very careful. So.
Spending money. That's a good point. Okay, which one of the go back to the Buick thing here, or the Oldsmobile thing. What is the final? You're looking at that. So was the 51 bad and the 29 bad and the 38 was normal? I mean, you can't just leave us hanging on the Oldsmobile. Most people on
So
here
two of them were okay, slightly down. One had dropped a lot, and it was a rental car, not me. It was my car I was renting, and one of them had got blown up at the garage. It just beat way too high. And so when I called up the rental agency, they said, I'd be fine, just leave it for a week. You've got the whole car for a whole week, just leave it, you'll be fine. Okay, right, let's get on with it. So they know what they're doing is the theory, and my knowledge on these things is relatively limited.
Yeah.
So.
Well, no, that's an interesting point. And Nathan, get ready to answer the same question. But Tony, that's an interesting point. The asset owner didn't really have a plan. It was like, it's going to be okay. Now, if that 51 pound had blown up because you hit a bump, right, or the other one had gone flat because it was going flat, the asset owner is sitting back somewhere. You're the guy stuck out there, and that is the correlation. Operators going, what am I going to do? I got a substation out in the north of London is dark. And guess who they're going to call? They're definitely going to call the asset owner, right? Yeah. So Nathan, same question for you as we look at this idea of data and data management.
Yeah, like the sentiment in Tony's comments makes a lot of sense. A lot of in terms of a strategy, right, a monitoring strategy. So a lot of utilities will approach the problem knowing that they just want better reliability out of their asset, and then they'll deploy monitoring, but then not understand the impact of that to their organization, like where the data is going, who will respond to alarms, how do you respond to alarms. So as part of a larger strategy, it is an important consideration to really think about what is your overall strategy for monitoring, okay? But then also for the asset manager and the use of data and the analysis of the large volumes of data, right? If we could just share on screen, Paula, the slide 1. So we're going to show an example of a kind of intelligent algorithm that utilizes data from multiple sources. Okay, so this is a real example of our algorithm that's processing data from the original online monitoring information. So in the upper left corner there, we see online trends of DGA information. So we can see clearly later in the trend, there's a sudden rise and some step increases in gassing, right? Now, of course, the monitor alerted the users to that condition, but just that bit of information alone, right, knowing that there was an alarm, doesn't determine the actions immediately. So, we have a few analytical tools kind of displayed here, but in the bottom left, you actually see what's called the DGA matrix, okay? And what that is an evaluation of the different concentrations of gas by different industry standard diagnostic methods. And you can see most of them indicate a thermal fault. There's some variability in the diagnostics. Different methods will determine different classes or outcomes for the type of diagnosis or the severity of the fault. But it is at least a clue. But you look at this. What does a thermal fault T3 mean actually? So the fact that the monitor detected something, it did its job, you're still not really any further ahead in terms of diagnosing the actual problem. So in terms of integrating a kind of holistic solution and having more information kind of working together in concert with each other to give a clearer picture of what the issue is inside of an asset, that's really what we're going for here. Okay, so the large circle wheel in the middle, like towards the middle, is it's a diagnosis tool of our analytical software. And when that data, the DGA information, is processed by this, it immediately throws a couple of suspected potential fault conditions. Okay, so that is very important because it at least equips the asset manager with the information to know these are potential areas I could look next. Okay, so there's a few suggestions for potential faults indicated by yellow, and then to a lesser degree or lesser confidence of identifying the other potential faults indicated by green. Okay, the green highlighting in the wheel. So you can see some of the suggested potential faults are overheated cellulose, overheated bare conductors, overheating structures, and then core insulation failure. So those potential identification of potential faults indicate to the asset manager, I should attempt these tests on the outage, okay? And that's what is one of the recommended actions here is the core insulation test. We can see above in the table where the arrow is pointed to, the yellow arrow, that 2 of the tests failed, indicating a short between the frame and the core. And then, it's pretty intuitive at this point, but you can have this tool and feed that data back to it, right? And then it diagnoses again. Clearly, there's a core insulation failure with a higher degree of confidence that that's the identified failure mechanism. So this is the type of visualization we have, the type of concept we have, that you should really integrate all the tests, all the monitoring data, all the maintenance that's applied on the transformer or any asset, and attempt to have this kind of decision support tool that a asset manager can use to help them determine the next step. But then when they have a larger body of data to do analytics on, to give a clearer picture of what the potential fault conditions are. Okay, so that's one example, one concept of how you can integrate this data. Of course, it's like a lot of it is like a logical model, applying logic and applying kind of correlations that a human expert would apply. But this is the type of tool that could be used for that type of purpose to integrate all the data that's being collected.
Tony, you have a comment?
Yeah, Nathan, it's a good example. I had a question about the step in the data and how long was it between the step appearing and the transformer being taken out of service? Because it looked as if it was about 10 days from the axis.
Yeah.
And so when you
Yeah.
play this through in real time, and I do have examples if you want to play, but where you have the data suddenly rises, to leave it in to get more data is a decision that has to be made or not made. As in, it's a default, we just
Yeah.
keep, we've got more data. But that step by itself should be an indication that there needs to be a plan in place to respond to, because you've had a big change in the DGA levels, but it was left in for another week or more. So I was just trying to work out how long was it left in and energized before it was removed.
Yeah, we could put the figure back up, but it practically utilities aren't always to be so responsive to take an outage, and it is a kind of assumed risk they may feel necessary to take in certain moments. We talked about the strategy and responding to alarms, like that is certain something that could be defined in the strategy. What change in gassing on a monitoring device do we respond and interrupt the unit immediately? Some of that should be managed through alarm management, right? You shouldn't be waiting on feedback from the diagnostic tool and the additional data that's collected over a time, but you should have criteria set out as part of your larger strategy when you take an outage in response to an alarm condition, and what the thresholds are for that. Yeah,
which is
Yeah,
the
maybe
plan
we'll,
he's talking about, right? Having a plan.
exactly.
yeah, maybe we'll get to a slide later I've got from a case of a bushing, and the owners of, I think it's about 70 transmission class transformers. They had a lot of the bushings which fail quickly, and they had the bushing monitor. When the bushing gave top level alert, operations had to switch a transformer out in 2 minutes. Now, these are transmission units, like trying to stop a battleship. It's a lot of work to do. They don't stop very easily. And so that was their written and agreed policy when they install a monitor. So that to me makes sense because they knew they were going to fail. They knew that they had this failure mode, and that's the trench bushing problem. And the plan was put in place when the monitor was installed, and it was 2 minutes. And admittedly, they did have some false positives, but they worked out why. And then the false negatives were avoided, and the false positives are the price you pay to avoid false negatives. And the result was they saved transformers, and they saved multi millions of dollars as a result, and they're still doing so now. But as soon as I saw that step, I'm like, why aren't we doing something right there? What was done then?
Mm-hmm.
And did they think, okay, we'll just leave it and see what happens? Because we've had that as well, and then it fails, and then people say your monitor didn't do anything. It's like, yes, it did. Look, it told you, and you hit the button saying do something. Acknowledge. Well, it's that plan has to be agreed and in place by all parties as early as possible.
Yeah.
You're hitting the point that when the equipment speaks, we are supposed to listen. And sometimes it speaks very loudly, and sometimes it speaks a little less loudly, but trending. And I think, Tony, that's kind of your point. When in the trend do you suddenly take a piece of equipment out of service? Because if you begin to see it, that step function, as you said, was big. And Paula, if you can put Nathan's slide back up there, that first step function was pretty large. I mean, if you looked at, and I can't read exactly what gas was, yeah, that first step function, you're pointing
Yeah.
to the top left. Is that correct, Tony?
Yep.
Yeah.
Yeah. So the initial step, both are in ethylene and in methane, are quite
Okay.
dramatic. So I mean, the ethylene increase already kind of outcompeting carbon may be a clue already in the DGA that, maybe this is a metal to metal contact that's causing the heating. But it's still not, it still requires the additional, evaluation, the additional testing to be confident to the failure mode. Um, I know we're going to go into machine learning and AI as part of the discussion as we proceed here, but I think there are some thoughts, that maybe you could have an AI applied just to trends like this and identify faults. And I tend to think that's unlikely, right? So the kind of guidance to first the warning from the monitoring system, then the kind of initial diagnostic, and the decision support, like what should we do next? I think those are all key elements. And I think you do need, SMEs working with tools like this to make those sort of decisions. So as a decision support aid tool.
We worked with a company, a steel company, Gerdau Steel. It was a Brazilian company, and they had at that time 30 some odd plants in the United States. Their furnace transformers, which are like the most important thing within a steel plant, they were monitoring DGA monitors on all of them. They had a subject matter expert there, but we came up with, and I say we, it was a company I worked for, and the engineer there came up with a simple way of doing it: alert, advise, and act. On the alert, we were responsible for. When the alarm went off, we got that alarm and we saw that, like, that first spike, that was the alert. The advise was, okay, now we are looking at this and we're saying, what should you do next? Because that's what everybody's going to say. Do I take it out of service, or do I continue to operate as it is? When you're talking about a furnace transformer, if you take it out of service, you've got molten metal that it's millions and millions of dollars to repair. So you know what plant management say, run to failure. Just keep running that thing, keep running it. We'll take it out of service at the end of this run. The run could be days, might even be weeks. So they're powering that thing up. So it was alert and advise. And in the advise phase, that means subject matter experts are looking and they're basically getting ready to act. And the act was do nothing or take it out of service. And the same is true when you talk about a utility. You either have to, route power so that the fewest number of people go without power, which gives them time. Fortunately, relay systems now can do that. But anyway, it's the idea that you get data. When do you act? And there's that sense of, Tony, what you're talking about is, should you have acted when it first spiked, or what do you do and what do you do? That's the hard thing for subject matter experts. If you have people that are not subject matter experts and they're just reliability or they're maintenance people, guess what? They're going to rely on you guys to make those decisions. Or as you say, Nathan, the algorithm, at what point do you take it out of service or do further testing? Go ahead, Tony.
I think Nathan's got a very good case there. It's an interesting example of the diagnostics coming in to support getting contextual data. The problem on the asset management side is if you take a transformer out because you found condition monitoring data that indicates a possible problem, and you go find a problem when you go and dive inside and you do all the testing, and that can happen, you get yelled at for the fact that you're not using the transformer to generate money somewhere.
Yeah.
If you don't take it out and it fails, you also get yelled at. And yes, I've been yelled at. So there are the two places that you really don't want to be, and you're stuck between them, the rock and the hard place.
Well, in your thing, you get yelled at whichever you do, so it really doesn't matter, right?
Yeah, and it's the decision maker isn't necessarily going to be an expert in the condition monitoring or the technical application or the individual measurements and the failure modes analyzed and what might be wrong. They're going to be someone, I usually call them the spreadsheet guy, who's got an asset health index and it says bad, therefore we must take the transformer out, or the breaker out, or the cable sealing in. So it does get to be a difficult decision.
So we've been talking about transformers. Before we get off of transformers, I want to look at the potential monitors that you could put on a transformer. Obviously, you can put a lot of different monitors. Is there a way to correlate the different, like, should there be a correlation between bushing monitoring data and temp and whatever DGA monitor that you have on it? Should there be a correlation, or are they just separate things, and you got to look at them and say, look, if it starts with a bushing monitor, as you were talking about, Tony, the failure started with a bushing monitor, we act to that. Would there have been a correlation that you could look at for DGA? Or is it, again, they really don't have a correlation? Let's start with you on that, Nathan.
Yeah, like we do really focus on correlating data and looking at multiple sensors to diagnose problems. There is a bushing case that I shared with Paula. Paula, if you could share the slide 2. Yeah. So yeah, so I know there's a lot of lines on the screen here, but I'll try to lead through. But the main point here is that there are certain defects that would be better identified, with the operating conditions. And there's a certain failure mode in oil paper bushings, particularly, that fails as a result of high temperature causing a reaction within the insulation system that leads to increased losses. Okay. I'm not displaying it on here, but that same defect also has some relationship to things like partial discharges. So, you can have two independent parameters or two independent sensors deployed on the bushing that would be indicating the presence of a defect, and that gives greater confidence. Okay. But in this case, the confidence is derived from the correlation with temperature. So here we have a thermally driven defect If you look at the middle trend graph, so the one in the middle with the heading bushing monitoring BM tan delta, so we see there during the kind of warmer summer months, a sudden rise in the tan delta on the bushing X1. Okay, it's drawn in yellow. And if you also notice at the bottom, there is the unit top oil temperature. So very clearly, there's a relationship there. And this mechanism is usually related to contaminants or moisture inside the bushing. When it migrates from the paper into the oil in between the layers of the bushing insulation, it becomes actively involved in producing losses and elevated tan delta detected. Okay, um, so clearly there's an understanding needed here for the type of defect and what drives it. And the case that Tony just made about shutting a transformer down and then not being able to find a problem, that's a very real risk for this type of defect, because once the transformer cools, you see top oil temperatures around 20 degrees Celsius, the losses are no longer active. They're not high. So if you shut down the transformer and you send a crew to do your regular power factor test, you may not likely detect a problem with this bushing. Okay, so in this particular case, we advised the utility that it was very critical, the timing between when the transformer was shut down to when they did the verification test with the power factor test. Okay, and that's what they did, and they were able to find that defect here. But it's really the understanding, and you can employ an algorithm for this to do this kind of correlation analysis. But if you have a correlation between temperature and high elevated dissipation factor in bushings particularly, that's indicative of a specific type of defect. And this defect can eventually fail bushings. We've seen also the progression and the deterioration over years where the losses become higher and higher, and eventually the bushing faults. Okay. The graphs on the right side actually plot on the vertical axes the capacitance, the relative change in capacitance, and then the horizontal, the power factor. And you can see, the difference, quite evidently, the difference between a good bushing and a bad bushing here, right? So these correlations with operating conditions are very important for identifying certain types of defects. And it's an example here of data and leveraging analytics to kind of detect a very specific defect type that you might not well detect in the regular maintenance testing, like the offline power factor test.
Okay. Tony, you've got a lot on bushing monitor. You mentioned that you've got a slide on that. I want to see that slide now because you're talking about bushings. And the first time I met you, you were talking about bushing failures at a conference. If you remember that, I can't even remember where we were.
That case, Nathan, is very interesting. It brings up a number of different aspects of bushing monitoring. One of which is the natural variation with temperature of power factor, tangent delta, capacitance. And so when we do bushing monitoring, we always do temperature correction, and the manufacturers will provide a temperature correction table so they can bring that in. But it's interesting when you compare one bushing in a set with the others in a set to see if one is acting differently. And it may not be above where it's supposed to be very much. But if it's different to the other two, then you have to start looking at, well, is it close to a wall where it gets a lot of sunshine and the other ones are getting more cool? What makes it asymmetrical? The important thing is that we have the context data to make a decision to try and identify what the failure mode is. Because if you can identify a failure mode, then you can get a timescale. So I've got a couple of examples where that's gone on. If I could go to Ola, please, slide number 15. And I've got lots of slides. Just want to make sure I pick out the right ones. And these are a subset of the Doble Life of a Transformer seminar, which was last week in Denver. And we go through a number of cases and we challenge people as to what would you do. But as ever, this is one of those cases where we're showing the whole story. When you live the story, you don't have the complete set of data. You're on the point where it's like, well, what am I going to do right now with what I know? And you can see from the table on the left, we're looking at H1, H2, H3, where H2 has already been swapped out because it was deteriorating. H1 and H3, we started monitoring those on the 27th of April 2008, so it's a while back. And you can see how the power factor on H1 rises. So there are some differences when you make a measurement online, because once your transformer is energized and your bushing's at an elevated voltage, the insulation itself is no longer at 10 kV or 12 kV in an offline test. And that online insulation is now at, say, hundreds of kV. And there's an effect called the Garden effect kicks in, and that can change the power factor that you see. In this case, this is unlikely to be the cause of that, because the two bushings, the H1 and H3, started very similar. And for some reason, H3 was quite content with where it was, and H1 decided to get upset. But on the right-hand side, you can see the online power factor, and this is just a relative power factor system. There was no reference voltage to do any confirmation. It is quite high for an offline test, but in an online system, this is not unusual. But the level at which it got to was the point at which was decided right at the outset, when it reaches here, we take it out. And they did the full forensics, and they confirmed that there was a problem with contamination in the bushing, which was leading to deterioration of the power factor. So this is just one of those cases, and you can see on the left the initial 0.26. Yeah, we're not too far from that to start with, but that H1 bushing has risen a lot. We didn't have a lot of context data on this one. There was very little in the way of given to us in terms of temperature. There was no PD. It was just a case of, we've got a bushing, we need to monitor it. And if the owners of this are making $50,000 an hour as a generator station online, they're going to put it in, because the cost of replacing the transformer, as long as they've risk managed it, is probably going to be a lot less than they'll make over a couple of months' time. So it's an asset management decision. If we can go to the next slide, please. So this is the one in Australia. This was a Doble conference paper 2013. And what we're looking at now is not a couple of months worth of data. This is 24 hours worth of hourly data. And we're just looking at the leakage current magnitude on 3 bushings, one of which is a trench bushing. It was as a result of this that we no longer do these measurements hourly on trench bushings. That was our default at the time. We do them every minute or two, just to make sure we've got some data and show a trend. But that transformer has 50% rise in the leakage current magnitude over 2 hours. This is not the point at which we start to have diagnostic discussions. This was Transgrid, and these are the guys who had a policy that said, when this comes in, top level alert, take it out within 2 minutes. And the alert came in on the right-hand side, and that's what they did. At that point, you've got a sustained degradation. It fits in with the failure mode, and the forensics on the right showed the tear in the insulation as a result of the manufacturing process. So 2 similar cases on bushings, but we always go for the what contextual data do we have available. Not always easy to find. Paula, if we could go and have a look at slide 29, that would be useful. This is just a quick one. And this is looking at partial discharge in the main tank of a generator step-up. It's a big step-up transformer, 660 MVA. It goes back to the 1970s. It is a well-used unit. And what we're looking at here is partial discharge over several days to weeks inside the main tank of the transformer. We do a statistical analysis of a spectrum to say, yes, there is partial discharge. We give an indication of how strong it is. This is not a phase resolve plot. And you can see this partial discharge rises and falls, rises and falls. And it was somewhat disturbing. It wasn't to the point where we were going to panic. The interesting thing was similar transformers on the same site had shown similar types of effect as a result of partial discharge from loose insulators on the isophase bus in the generator station. And it was intermittent, the same way this is intermittent, but this is right in the main tank. If we could go down one, please. You see that this correlates, sorry, they changed color in the slide here. To a gold is the partial discharge and the blue is tap position. And mark one eyeball, you can see when the tap position rises, in general, the partial discharge rises with it, and when the tap position falls, PD comes down. That's a very strong indication that we need to be investigating the tap changer, which was planned. And so the technical decision was to go and investigate, see if we've got any loose contacts, see if we've got any worn away, if the spring has failed, so on and so forth, a whole bunch of different possibilities. The interesting thing was the day that they had the outage to take this out and investigate, drain the oil, they were halfway through draining the oil when grid control rang up and said, can you put this back in service? We need you online to support the grid. It's an asset management decision. And they said, yes, we can. And so even though it was in a condition that they had then identified as a problem, they filled it up, put it back in to do its job. But that's an asset management decision with context data and expertise behind them, an informed user. So just an interesting case.
And if it had failed after they did that, you'd have gotten yelled at. And if you said you couldn't put it back in service, you would have gotten yelled at. So your point about no matter what you do, you're going to. But it is the responsibility of the asset manager to set the parameters and to kind of set a course of action. Otherwise, we're going to be flying blind. And the best situations I've seen in my time in this industry are when there is very clear expectation from the asset owner, or let's just say the asset manager, and the actual on the ground people, both a company like Doble or a company like Camlin Energy, and then the operators on the ground. We got a lot of questions, and we only have 13 minutes to get to them. But I do want to go to one, and you kind of mentioned it a little bit, Nathan, and I'm going to start with you on this one, Tony. AI and ML. If I've heard it once, I was at a conference last week and one earlier in the year, and all I heard was AI and ML. And I didn't see an example of it in power systems. I heard a lot about it, but I never really saw a good example. The best one I saw was at Southern Cal Edison. They used to take substation transformers out and they would replace them based on age. They did a back testing and they said, what if we had some other factors? And they chose 8 other factors. They did not have DGA monitors on it, so they really didn't have what I would consider the best factors. But they took things like condition of they actually took humidity of the substation because they could track that. They took a lot of different things. And when they changed and said, let's do it based on condition as opposed to age, the first year they would have saved $2.5 million because they would have taken some transformers out that failed and they would have left others in that didn't fail. And so they were doing that. They moved it forward and said, now we're going to use that. And the next year they saved $4.5 million. Now that wasn't AI. That was simple machine learning. They just took some data and said, yeah, what does that mean? What are your thoughts about AI and machine learning for this whole monitoring and diagnostic world?
Let's start with slide number 30, if we could, Paula. My own view is that I did a PhD in this 30 years ago, and I know everything. But that's a really bad place to start from because I don't know everything. I know a little bit based on what I knew. And AI is here to save us, depending on who you talk to. So these are 2 people who got, in the UK, for that car, KN19TER, a fixed penalty notice for driving in a bus lane. And they said, we're looking at this, we weren't anywhere near this bus lane. And the UK's got lots and lots of places where you can be automatically fined and they send you a ticket. And they did. And they're like, okay, show us in the bus lane. Please, show us driving this car in the bus lane. So the next one down, please, Paula. And what they showed was, hopefully, this is a lady with a sweatshirt that says knitter, and his KN19TER looks like it's there. So somehow they've identified the number plate, license plate, whatever you want to call it, and then not done the bit that says, but is this attached to a vehicle? What they've done is said, we found this, therefore it must be the car. And it's that common sense piece which is often missing from the whole approach to AI. So next slide, please, Paul. One of the things that we did, looking at just, for example, partial discharge analysis, was taking phase resolve plots, which are beautiful little pictures, and saying, can we differentiate between the data from problem on the surface, problem within the void, problem somewhere else? But the first thing we wanted to do was make sure that we said in the machine learning, does a new piece of information look like something we've seen before? And it was Chomsky, Noam Chomsky, the linguist, who said machine learning is unique in science in that it defines success as being to approximate previously unseen data. So we've got these nice patterns, and what we're looking for is a thing called an OOD. Does this look like what we've seen before? Can we give it a measure of, before I even think about trying to classify it, does it look familiar? If I've been looking at sheep and goats and someone shows me a picture of a crocodile, I should say, that doesn't look like a sheep or a goat. So for the next one down, please, Paula. And these are just two examples. This is a 106 MVA turbine. It's a GE. This does not mean it will work on any GE device. It does not mean it will work on 112 MVA or other similar. It was for this set of data. And at the top left, you can see some data comes in. It says, is it in distribution? Yes, it is. It's got a similarity score, the SSIM of 0.94. It's a statistical measurement. And on the right, you can see that it gives you some different diagnoses, but it's most confident that it's one particular thing, partial discharge between phase A, type A. For the second set, it says, this does not look familiar. That's similarity effort. And that's a very important thing to do, is identify that, because even though it didn't look familiar, it was extremely confident in its analysis. It was up at 85%. It's one of these. Now think about if I have sheep and goats and I show pictures of it and I show you a llama, it will look a little bit like a sheep and it will look a little bit like a goat. So there's no surprise it gives you two classifications. If you could go down two, please, Paula. One example of where this has been successful, past that one, please, is Duke Energy. And they were given a whole data science project with a very well-known Northeastern University in the US, and they did a lot of work. And what the data scientist said to them is, your data must be wrong because it doesn't fit our models. There's a guy called Tom Rhodes at Duke said, at which point we thought this is never going to work. But what they concluded was to do exactly what you were saying, Alan, where the top left is the engineered analysis. You use every known dissolved gas analysis tool, everything Nathan showed before in terms of what a standard analysis for DGA, for temperature, for SFRA, for leakage reactant. They did all of that, used all of those, identified from that what seemed to be good data and bad data, input and output, and then combined that with the original data so that they then had a machine learning system which would then give them an output and classification. This they found useful as it would identify edge cases that were not previously identified. So this practically supported the SMEs, and they were very clear that this was not to take the SMEs' job away, but was to help identify those things that might otherwise get missed. There's a couple of technical papers at Doble conference on this one. It's really, in one way, very simple, but another way, it's quite elegant what they did. So that's where I see things going, is making sure we know what we're doing and not cutting people out of the loop just yet.
No, that's good. That's a great slide. Thank you. Nathan, comments?
Generally, I would agree. I think a lot of the excitement around AI and machine learning in recent years is around these large language models. And those don't adapt well to computation, calculation, applying logic. They're not strong with mathematics, so they don't really generalize well to the types of applications we have for analyzing data on assets. Okay. And another complication is the slide there that Tony showed, where they employed supervised machine learning. Now, supervised machine learning is where you know the outcome. You're training on a data set where you know the final outcome. And I think for things like transformers and assets, although there's a large volume of data, we're collecting monitoring data. There's chemical labs that have many examples of DGA data. There isn't a broad data set that has these known failure modes, known failure cases that would generalize well to the larger population of transformers. There's a lot of variables, with manufacturers, with different oil types. Even for the monitoring devices, there will be variables in the sensitivity and measurement uncertainties for the monitoring data. So with all these variables, the ability to point and train a model to identify exact defects, known defects, based on the input data provided, it would be very hard to associate and connect those two dots, okay? Now, I do think there's a good place for anomaly detection, at least on a per asset basis. So if you're collecting data on your transformer for many years, you kind of know what its behavior is in terms of seasonal variation, loading variations. You're going to have some predictability for how much the losses fluctuate in the bushing predictably, what the incremental gassing rates may be for different operating temperatures. And those things can be hard for humans to perceive. And I think that a machine learning algorithm could assist with that sort of thing. But the concept I think that we'd like to promote is this concept of augmented intelligence. So not to move full-fledged into AI and throwing lots of data at an AI, but really to have the AI identify if something is different in an asset than previously, to flag suspected failure modes, and then still engage the subject matter experts so that they can, make an informed decision, knowing that there was a potential anomaly or a potential fault condition in that transformer. And that relationship, it's beneficial because the human expert doesn't need to review necessarily all those results where there is no anomaly, where there is no problem, and they can focus on the ones where there is something, some oddity in the data.
We have a lot of questions. Unfortunately, we only have 3 minutes left. So I'm going to ask one question. Thank you so much. I mean, there's I guess I should have realized that you all would come prepared. And as you did, you came prepared. You've got the right slides. I'm going to ask one question, and it's really probably the most important one, because there's a lot of things about specifics, like about high voltage DC converter transformers, things like that. We will send those questions to our experts and they can answer them for the people that ask, because we do know who asked them. But let me just, this one, we hear a lot about digital twins. The idea that you've got this thing that looks like this thing in the real world, and what happens in the real world you can then track in the digital twin. And then in the digital twin, you can begin to do predictions. What ifs, then what would you do? Real quick, your thoughts on digital twins, and you really only have 1 minute. Tony, you got 1 minute, then Nathan, you got 1 minute to close it down. Good or bad?
Paul, if we could put slide 34 up, please. There is a CGRE working group on digital twins for power transformers, which I'm involved with, and I specifically got involved with that for looking at the reliability of digital twins. Ultimately, a digital twin is a model of a real transformer. That was slide 34, please. And to quote a statistician, all models are wrong. Some models are useful. And the question is not whether it's wrong, but how far wrong can it be to be unacceptably wrong? So a digital twinner, we like them, they're very useful, but they're always wrong. And people will think to themselves, no, not all models are wrong. If you ever look at Google Maps on your phone, it will give you a plot of a line between, for example, so the picture here, if you could show the picture, please, Paul, down one. You could, in this case, we're looking from the town of New Delhi, and we're going down to Agra because I wanted to go on a day trip, visit the Taj Mahal. And everyone understands what this is. Everyone understands that this is a route along the available roads, and we get times for it. But what we don't usually think about is the fact that if that scale is correct, then that blue line means that that road is about 3/4 of a mile wide. So it's wrong, but it's acceptably wrong. In everything you do with a digital twin, you have to look at, is it acceptably wrong? Because if it isn't, then it's an evil twin and not a saintly twin. So digital twin's great, and it's a case of, are we doing it just to mimic, or are we doing it to make predictions? That's the first thing. and then how accurate are they? Sorry, that's my minute done.
Nathan, unfortunately, you don't get your minute, my friend. Our time is up. Tony McGrail from Doble, Nathan Jacob
Sorry,
from
Nathan.
Camlin Energy. Let's do this again because there's a lot more for us to talk about. This has been an APC Media broadcast. Thank you, gentlemen.
Thank you.
Thank you. Thank you, Nathan.